Like resistors, capacitors can be used in more complex circuits. And so we'll talk today about how capacitors get used in series and in parallel, and now how that changes their attributes. So we need to do the same things we did with resistors in terms of thinking about how they work in circuits. And so we're going to talk about parallel capacitor circuits and series capacitor circuits. Okay. So here we have some capacitors set up in parallel, and there's some interesting physics here. Um, we often want to know, again, just like with resistors, we want to know what the equivalent capacitance is, just like we wanted to know what the equivalent resistance was. So when I set up this circuit with 3 capacitors in it, how is that going to change the capacitance? How much energy am I going to be storing? In parallel, this is the easier one for capacitors. Basically, we can think of these capacitors as extensions of each other, right? What's the plate area matters a lot. Well, really, we're just adding more plate area, okay? We're just adding more area for that charge to be. Just like with resistance in parallel circuits, our voltage here and here is the full voltage, right? Because we know along this wire, everything's, at 12 volts, say. And we know along this wire, everything's at 0 volts, right? So here to here is 12 volts, here to here is 12 volts, here to here is 12 volts. And if that's the case, right, and our Q, our charge is going to be voltage times capacitance, we're not losing anything, right? Because our voltage, we have the full voltage for this capacitance and the full voltage for that capacitance. So that we can just add up all of the total uh, capacitance for the total charge for these. The total capacitance is also going to be the same because essentially we're multiplying all of these by the voltage and we get this because that voltage is the same for each capacitor. So if you wanted to increase your capacitance, but for some reason had limited, space, or you wanted to use smaller capacitors, you could do that just by setting them in parallel. But what happens when we arrange them in series? Now this is a kind of interesting situation. Look at our red square here. So what is this? This is unconnected to the battery, right? There's no charge crossing here or crossing there. This is neutral. So any charge that gets pulled onto here has to be matched by the positive charge here, right? So if we get negative 10 units here, we're going to have a positive 10 units here. It's always going to have that neutral charge. Now, what does that mean? Well, it means that the charge on here and here, right, on C2, if this is 10, this can't be any bigger or smaller than 10, right? It has to be 10 too, okay? And if this is 10, negative 10, then this has to be positive 10, right? And if this is positive 10, this has to be negative 10, okay? What that means is the smallest, the charge here, so all of these Q's are going to be equal, opposite in sign in some cases, but equal in magnitude. It can't be any bigger than the smallest capacitance, okay, or the smallest Q. So if I have 2 really big capacitors here and one small one down here, the overall capacitance of this circuit is going to be actually a little bit less than my capacitance here. So yeah, it limits the maximum capacitance to all the capacitors since the charge of each capacitor will be the same, and I can't get bigger than the maximum charge of my small capacitor. And so to calculate this, the capacitance, we do that inverse summing that we did for parallel resistance. And you might ask, well, why would you do this? Why would I add extra capacitors in series? what I was getting was a lower total capacitance. And it's mostly for safety, right? So if this one accidentally discharged or something, like, and I just had one capacitor in this series, then I would get a big charge moving through this circuit very quickly, which could create all sorts of problems. But if in this situation, if that accidentally discharged, then basically it would be as if I now only had two capacitors in series. You wouldn't get that full breakdown of the circuit. So you see capacitors in series, mostly for a safety reason. Now we get to combine resistors and capacitors into a series. And this creates all sorts of interesting things. Mostly we've been talking about when we say a capacitor gets charged, we assume that's going to happen immediately, right? If I don't have this resistor up here and I connect to this switch, all of a sudden this is all going to, my battery's 12 volts. This is all going to be 12 volts. This top plate is going to be charged to 12 volts and this will be charged to 0 volts. We think of that as happening immediately. But if I put a resistor here, it's going to slow it down, right? The current moving from here, my initial 12 volts to my initial 0 volts or, middle 6 volts, is going to move through here more slowly and it's not going to charge that plate immediately. Why is that useful? Well, it can be useful in a couple of different capacities because sometimes you want to use a circuit like this to actually time something. So let's actually use negatives and positives here. Let's say I have this 6 volt and this is negative 6 volts, right? We can say that because what matters is the voltage difference if I have a 12 volt battery. This is initially charged at 0. This is initially charged at 0. When I open that switch, I'm going to get current moving through here. Initially, the voltage difference between this and this is going to be 6, right? This is 6, 0, and negative 6. As this charges, it's going to climb, right? It's going to go from 0 to 1, 2, 3, 4. By the time it gets to 5, I only have a voltage difference of 1 across here, right? And my current is going to slow down. So it's going to go quickly at the beginning, and then the voltage difference is going to go down, and I'm going to get a smaller and smaller voltage until this is fully charged and is at 6 volts. And at that point, this is at 6 volts, this is at 6 volts, and I won't have any current through there. So that's why you get a slower charge when you put a resistor into one of these circuits. We can actually chart what's happening to that. Let's actually look at the next slide. We can chart how that's happening by looking at an exponential curve like this. So again, let's say our E here was 6, right? And our initial voltage here was 0. This is what's going to happen to the charge on the capacitor, right? It's going to start at 0. It's going to quickly go up to about halfway, and then the voltage across here is going to get smaller and smaller, and then it's going to slowly asymptotically increase towards the full voltage of 6. We can time that by looking at this number tau. And tau, the time constant, is R times C, is resistance times capacitance. This, when we multiply, our units are time, right? So a number of seconds. And that's going to tell you when you get to this point, 0.63 times E. So if we had that 6 volts here, by the time we got to 3.6 volts, it would take us time tau. Why is that? Well, if my capacitance is large, it's going to take me longer to fill that, right, for a given voltage, because I got to move a lot of charge over there. If my resistance is large, that charge is going to move more slowly, right? So as R or C grow, the time it takes to charge is going to grow too. But these are components. I can pick out the resistance I want. I can pick out the capacitance I want. So I can control very easily what tau is for a given circuit. I can then calculate, this is an exponential equation basically describing this curve. I can calculate what my voltage on the capacitor at any given time is with this equation here. At time equals 0, right? What's my voltage on the capacitor? You'd expect it to be 0, right? Because we're saying, well, that at the initial point that its voltage is 0. Right? So 0 over RC, that's always going to be 0. E to the 0, anything to the 0 is 1. 1 minus 1, so this term is 0. And so it's going to be 0 times your EMF. In other words, your initial voltage is 0. This guy, if this is negative, if I let this charge for a long time, this becomes very large. E to the negative infinity is 0. 1 minus 0 is 1, and then it becomes the full EMF. So you can see how that equation works. Now we can do the same thing. We could, if we took we fully charged it, and then we took the battery out and wanted to let it discharge, we'd see the same kind of curve, just flipped on its head. Okay, so in this case, we take the battery out, we connect a circuit, we've got some energy stored on this capacitor, right? And then we flip a switch that allows the current to go back to even out, and it's going to be controlled by that same RC, right? If R is big, it takes a long time for that current to get through. If C is big, there's a lot of current that has to get through.